orbifold, or two-dimensional orbifold. So the geodesic flow on a hyperbolic two-dimensional orbifold admits infinitely many open book decomposition, while supporting open book decomposition. I will write it like that. Open book decomposition with genus-one pages. Okay, so infinitely many, it's not only up to the mapping class group of the surface, if the surface has infinite mapping class group, but it's infinitely many non-isomorphic. So I will explain a bit later, but so you have infinitely many open book decomposition whose pages are tori. So not only one, but infinitely many pages. Well, there will be rational. I think that well, I didn't check, but I think that you can have infinitely many open book decompositions. But that's right, we only prove. No, well, it's infinitely many open book decompositions. There is no, you can, yeah, okay. I will maybe precise this a bit later, but you can even have infinitely many. Okay, and the second theorem is not yet on the archive. I can say right now why, because well, some part of the proof relies on some computer calculations, and I would like to get rid of these. So far it's a computer-assisted proof, and I have hope to remove this aid of the computer. So that's why it's not yet available. But so the second theorem is if phi is a transitive Anosov flow in dimension 3 in a 3 manifold. If phi admits a genus-two open book decomposition supporting open book decomposition, and there is an additional assumption, and the monodromy is what is called H2. So it's an assumption that the monodromy will be a pseudo-Anosov map, and it says that this the invariant foliation of this pseudo-Anosov map has only one singularity where the total angle is 6 pi. There could be several possibilities for the singularities, and here we have a restriction on the singularity. So there is a restriction on the first return map. But so if you have a transitive Anosov flow with a genus-two open book decomposition, then actually phi admits a genus-one, and infinitely many genus-one open book decomposition admits a genus-one open book decomposition. Okay, so now maybe I will give a bit of context and define the terms and motivate these statements. So maybe I start with an open book decomposition. So in general, well, probably everybody, I don't know whether everybody knows what an open book decomposition is. I will just recall quickly. An open book decomposition for a manifold, for a three-dimensional manifold M is, yes? H2, sorry. H2, so H2 means it's a strata of a quadratic differential or abelian differential in this case. It means that the singularity, there is one singularity where the total angle is 6 pi. Sorry, it's twice this. So it means that if you look at there is a singularity, and if you look at the invariant foliations around this singularity, there is a total angle like this. So this is the singularity. You know that there are several possibilities. You know that the total angle add up to the total excess over 2 pi add up to 4 pi. So either you put all the excess in one point, or you dispatch it between 2, 3, or up to 4 points. Yes? So here, do you understand what I mean? Yes. So when you have when you have a pseudo Anosov map, you have some invariant foliations, and this is a singular foliation. And here, what I ask is that there is only one singularity for these invariant foliations, and not 2, 3, or 4. Yes. Yes, the singularities are actually on the boundary of an open book decomposition, since I assume the flow is Anosov, as what you may guess, but it means that all the singularity is around one boundary component and not 2, 3. Yes, I have actually it's a 6-pronged. Yeah. Oh, sorry, it's not. The picture is not that one yet. The picture is that one for the. So here. Exactly. So what happens is that actually you blow up this thing, and this will be a boundary component. So maybe it means that there is one boundary component here where it looks like this around. Well, if you have so here actually what this assumptions contains also is that the transitive Anosov flow has orientable invariant foliations. So this is a restriction. And then among those Anosov flows with invariant orientable invariant foliations, there are in a sense two classes. If you have a genus-two open book decomposition, either you are in H2 or in H11. And H11 would mean two singularities with angle 4 pi. So we could say that we treat half of the cases. If you speak to someone specialist in a pseudo Anosov, he will say that the other class is the generic one, so that one is a bit more restrictive. So far it's a bit restrictive. I mean, there is hope to extend this to H11, but it's just that the computations are much heavier. So well, I don't know. The conjecture is that, okay, I will give the conjecture in 5 minutes. So, okay, so I just remind quickly what is an open book decomposition. So an open book decomposition is a pair K F, where K is a link in the manifold, and F is a co-oriented foliation, two-dimensional foliation of the complement of the link, such that with two assumptions, such that the pages. How did I write that? Well, the leaves are surfaces whose boundary are compact. I will say, okay, are interior of compact surfaces with boundary inside. Okay, and there is a local model, and with local model around K, so around what is called the binding. So this link is called the binding. Around the binding. So K is a link, so it looks like that. And we ask that the pages, well, the pages look like the pages of an open book. So I guess most of you know this picture. Okay, so Vincent asked about the multiplicity. The thing is that if you take one page, it's a surface, and it may arise either it arrives once around K, or it may so several pieces of your page may come around K. In which case we say that we have a rational open book. So one page could come like one locally around the binding. It may arrive once or more than once. There could be three local pages corresponding to one global page. Sorry? Yes, and moreover, yes, here I say that, And when you glue the top and the bottom, because K is a knot, there may be some rotation, some twists. So that's why. So that could be one boundary component of the surface, which arrives, but with multiplicity 3 around the boundary. This could be, well, I like to allow this, although I guess that in the first statement, at least, we can get rid of that. Okay, so this is the general thing of what is an open book decomposition. And now I will say what is an open. Suppose that you are given a non-singular vector field on M. We will say that an open book decomposition is adapted to the vector field. So what we will ask a few more things. We will ask that the link is actually made of periodic orbits. So the binding, we ask that the binding is tangent to the vector field. Yeah, so since it's a link, it means that it's a link made of periodic orbits. And we will also ask that the pages here, so I say it's a co-oriented foliation. Well, now we will ask that this foliation is transverse to the vector field. So here I will say that it has to be transverse to the vector field, meaning that here, if you have a page, the vector field is really transverse to this page. Okay, and there is we ask this, and now we add a third condition. We want that every orbit. Okay, I will say it like this: through every point of M, the orbit if I write phi x for the flow of the vector field, and if I take a point in the manifold and I look at the orbit of time t, then I ask that this intersects all pages of the open book. Intersects all pages. So there exists a t positive such that for all p in the 3 manifold, the orbit of length t intersects all the pages. Thank you. For all p outside k. Well, for k, it's also true. Well, it intersects the closure of the pages. But yes, okay. So this is what we call a supporting open book for a vector field. Now the connection with, well, maybe I can first give an example, and then with the eraser. Okay, so the easiest example of this is if you take the hop flow on S3. So the orbits are circles, and we know that they are linked, that they all have linking number 1. So if you take the hop flow here, if you take one orbit of the hop flow, so one periodic orbit of the hop flow, it bounds a disk. So here, this orbit bounds a disk. And actually, this disk is transverse to all orbits, which is not really surprising because we know that they all link once. So this disk here, we see that its boundary is one periodic orbit. Inside, well, you have to check this, but if you really take the flat disk here, it's transverse to the vector field. And we see that the first return time is, well, say 2 pi, if we take the standard parametrization. So there is here the big T is 2 pi. After time 2 pi, every orbit intersects this disk. Yes. Okay, so this is an example of a supporting open book decomposition. Okay, and so, well, a motivation for this is the theorem by Emmanuel. Well, it's maybe not the only motivation, but it's an important motivation in the domain of contact topology, that every contact structure, so every contact structure, I don't admit a contact form whose rep vector field so I will write it R lambda, admits supporting the open book decomposition. So, well, it's not the most general statement, but it's the one that interests me here. So you take an arbitrary contact structure, then there exists a contact form whose ray vector field admits a supporting open book decomposition. So, for example, the example of the hop flow here works for the standard form on S3. So the ray vector field for the standard tight contact structure, contact form on S3 is the hop flow. And so this is a supporting open book decomposition. Okay. Yes, I wanted to give a second example. Okay, and now, well, maybe I can now raise the question by Etnyre. Well, the definition due to Etnyre is the following. We will define for Xi a contact structure. We define the support genus. So SG of Xi to be the minimum over all contact forms of the minimum of all open book decompositions supporting open book decomposition of the genus of the pages. So the genus is the genus is the genus of a surface, and so you consider over all possible open book decomposition the one whose genus is minimal. So, for example, here for the tight form on the sphere, we have a disk. A disk has genus-zero, so that's it means that the support genus of this form is 0. Yes, and well, then the question is, what can you say about the support genus? Okay, so there is the theorem by Etnyre proved is that if Xi is overtwisted, well, I don't know enough. I don't know whether he proved it or whether it was a corollary or something already known. Patrick, you know. If Xi is overtwisted, then the support genus of Xi is equal to 0. Okay. So this is one case where we know. So in this case, it means that we have quite simple open book decompositions. Well. So the pages has genus-zero. We don't know what is the number of boundary components. So the topology may not be that easy because it could be a disk with many holes, but at least it's a disk. I mean, I don't know. I don't. Well, no, doesn't matter. Okay. So well, then you may ask, what do we know about other forms? So here, for example, it's not an if and only if, because this is an example of a tight form which has support genus-zero. So you may ask, what can we hope? And so yes. Do I explain this example or not? Well, maybe not. Okay, so there is a construction of Fried, which goes back to Birkhoff actually, which tells you that if for sigma a hyperbolic surface, there exists a supporting open book decomposition for, well, so either you say it for the ray vector field, so for the geodesic flow, for the geodesic flow on the, well, either you say the unit tangent bundle or the unit cotangent bundle. So either for the geodesic flow or for the co-geodesic flow, there is the supporting open book decomposition whose pages, so with genus-one. Yes, so it means that, for example, for the standard you will form on the unique tangent bundle, the support genus is 0 or 1. And actually, I realize I'm not sure I can prove that it's not 0, but it's not 0. I think it cannot be 0, but it's.
You have a symplectic feeling with disconnected boundary for the higher.
Yes. Yes. So yes. So thank you, Patrick. So here the genus, the support genus is indeed 1. 0 is not possible. No, it's yeah. So the question, okay. So the question by Etnyre is: do there exist contact forms with support genus at least 2? Okay, so up to today, we don't have examples of contact structures for which we can prove that the support genus is larger than 1. So either we don't know what to say, or we can find an open book decomposition with genus-0 or 1 pages. Okay, so now I will switch with my main interest, but which is connected to this, which is Anosov flows. So I just recall quickly what is an Anosov flow on a 3 manifold. I will give a topological characterization, which is known now to be equivalent to the standard definition. What is an Anosov flow? It's a flow, it's a non-singular flow, such that if you take an orbit, this orbit lies at the intersection of 2 leaves of a foliation. So there is a foliation of the 3 manifold, but by what are called stable and unstable leaves. So this is a stable leaf, and this is an unstable leaf. Okay, and what is the property? That this foliation is invariant by the flow, and if you have an orbit, say, in the stable leaf here, it converges, well, exponentially fast. It converges to the orbit you started with, and in the unstable leaf, well, it converges in the past. So if you reverse time, you converges toward your leaf. So this is you could put quantificators, but actually, if you only take the topological characterization that I just gave, it's now a theorem by Mario Shannon, so from last year, that this is equivalent to the standard definition. Okay, so this is what, so Anosov flows, there are examples of Anosov flows. For example, if you take the geodesic flow on the unit tangent bundle to a hyperbolic surface, this is an example of an Anosov flow. This is Anosov examples of an Anosov flows. But there are many Anosov flows in 3 manifolds that are not of this type. Yes, and so you can ask exactly the same question. When you have an Anosov flow, is there a supporting open book decomposition, and what is its minimal genus? So there is a theorem of Fried from 82 that every transitive. So transitive means that there is a dense orbit. And it's not at all free. I mean, there exist non-transitive Anosov flows, but here I only consider transitive Anosov flows. So every transitive Anosov flow admits a supporting open book decomposition. Yes, and actually, I did not explain the example of Fried-Birkhoff here, but it's really, this is an example of an Anosov flow. So here in this example, we have genus-one pages. So the hop flow is not Anosov, but we have some Anosov flows. And so Fried made a general construction, which doesn't control the genus at all. And just on the example he had, he found genus-one Birkhoff open book decomposition. And so he raised the question in the same paper, does there exist a transitive Anosov flow with a support genus? So if I at least 2, which means that there wouldn't be any genus-one open book decomposition. So this is Fried's question, and this is still a conjecture. And the theorem, the second theorem I wrote, was a small step in the direction of a negative answer to this question. So because I say that if there is a genus-two open book decomposition plus an assumption, then there is a genus-one open book decomposition. So the conjecture would be that there is always a genus-one open book decomposition with the same strategy that if you have a genus G, then you have a genus G minus one and you have an induction. That is the hope, but so far it's far from proven. Okay. So I wanted to give some hints on how we prove that because I hope it's interesting and it can be maybe exported to, so what I did is for Anosov flows, but in a sense, I hope that part of these methods and ideas can be exported to contact structures. In particular, we know that every contact structure, well, either it's quite simple, but I think even for simple ones, there exists. So every contact structure admits a supporting open book decomposition, and it's not, you can also ask that the monodromy is a pseudo-Anosov maps, a pseudo-Anosov map. So here I didn't deal with pseudo-Anosov flows, but only Anosov flows, but some method can be exported to Anosov flows. And so these, the statement we have here for Anosov flow, we can then think about pseudo-Anosov flow, and then this would in particular give some information for contact structures. Okay, so that's the connection between these two topics. Okay, so let me give some ideas and hints about how we deal with this. So the first remark is that I presented everything in terms of open book decomposition because this is what is most known in contact topology. But actually, what interests me is just one page of the open book decomposition. Because if you have one page of the open book decomposition, what is called global surface of section by some people and Birkhoff section by other people. So we can say that sigma is a, okay, so we say that sigma is a Birkhoff section. So a surface is a Birkhoff section for a flow. If we have more or less the assumption we had, but it's just that instead of finding the whole foliation, I will just explain that it's enough to find one page of the foliation. So the first thing, so a Birkhoff surface for a vector field is a surface such that the boundary of the surface is tangent, is a finite link of periodic orbits of X. Yes, so the boundary is tangent to the flow. The interior of the surface is transverse to the vector field. And there is a well-defined first return time, which can be said, which can be summarized by there exists a time t such that if you flow the surface for an interval 0t, then you cover the whole free manifold. So you start from your surface, you flow it for some time t, and then you cover the whole manifold, so all points are covered. So if we have a Birkhoff section, then by pushing it along the flow, we obtain the whole foliation and the whole open book decomposition. So it's enough to find what is called the Birkhoff section. Okay. Now,
the interior is embedded, and you ask nothing.
Oh yes, I didn't ask. Yeah, sorry. So maybe I should have recited. Yes. So the interior is embedded, and the boundary is immersed. So the boundary, I should have said that the boundary is immersed. Yes. So the boundary may travel several times along a periodic orbit, exactly as we explained for an open book decomposition. So this is what we are looking for, and when we have this, we are happy. And so we want Birkhoff sections, and we want to control the genus of the Birkhoff sections. Okay. So maybe the first an important tool is that when you have a Birkhoff section, and actually a bit less than Birkhoff section, when you have two transverse surfaces to the flow, so assume that S1, S2 are transverse to a vector field. So they have boundary, they are transverse to the vector field, and their boundary are tangent to the vector field. So it's the same, but just I dropped the third condition in this first remark. So the boundary are tangent to the vector field. So if you have two surfaces, so I will make a picture away from. So if you have two such surfaces, you can always put them in general position. So when you have two surfaces in general position in a three manifold, they will intersect along arcs or circles and maybe triple points. I mean, there could be triple points. The remark is that along these singularities where you have these two surfaces, okay, so if you have two surfaces, here a green, here a red one, if they are both transverse to the vector field, there is a direction of the vector field. And so what you can do is to resolve this intersection transversally by keeping transversality to the vector field. You can resolve this. So now the color are not anymore meaningful because it connects the surfaces. Yes. So when you had two surfaces, now locally you have two leaves. So you have a singularity which looks like an X, and you resolve, and the vector field is vertical. So transverse. So it's like an X cross interval, and you resolve it transversally to the flow by obtaining two leaves. Okay, so you can do that. Then you have to look at triple points, but triple points you can do that inductively on all lines of intersections. That's one way of doing this. And so the conclusion is that if you have two such surfaces, you can consider what we can call the Fried sum of these two surfaces, because well, this construction was first explained by Fried.
What do you mean by triple points? The two surfaces are not embedded in the beginning?
No, they were embedded in the beginning. Just what? Oh. Oh, yes, you are right. If there are two surfaces, there are no triple points. That's right. Thank you. Yes, okay. If they were only immersed, then we would have to resolve this. But since they were embedded, we don't have to resolve this. Okay, so this way, away from the boundary, maybe I can say a word about what could happen around the boundary. There are several local pictures, but for example, you have one surface with boundary here, so which is a half plane, and the other surface locally is like a disk transverse to this half plane. And so the intersection here is an arc that terminates on the boundary of the first surface. So you have one half plane, vertical half plane, and one disk transverse to the boundary of this half plane. And the flow, so here the flow is tangent to the boundary of the first surface, but it's transverse to this arc of intersection, and it's transverse to both surfaces along this arc of intersection. So this desingularization I explained along an arc of intersection, you can extend it along the boundary, and this will actually give something that will look now like a helix. So the union of both surfaces after desingularization, it will look like an helix. I don't know whether the picture is really explicit. You have to think a bit about it. But say you open here this interval into, the thing is that this interval of intersection, you will open it and you will cut the half plane into two quarter planes, and you will cut the disk into an open disk, and you will connect these leaves together. So this will give something like this, then a helix which rotates. And then, well, anyway, what I want to say is that there is a nice desingularization here process. And concerning the support genus, what is interesting, so, okay, I didn't say, but I just wanted to say that starting with these two surfaces, you obtain what we call the Fried sum, which is again a transverse surface. Yes, so there, in a sense, there is a monoid, not the monoid, a lattice, because there is no neutral element. There is a lattice structure on the set of transverse surfaces, which allows you to take the sum of two such surfaces. Okay. Now, when you do this operation and you care about the genus, you want to control the genus, and the genus can be controlled in this process. And there is one thing is additive during this process, but you have to define it properly. What is additive? So given these two surfaces S1, S2, I will define what we call the punctured Euler characteristic of one surface. What it is, it means that I have a surface S1 which has some boundary, okay? but it intersects the boundary of S2 along some points. So this is the surface S1, and there is the surface S2, and in particular, there is the boundary of S2. Yeah, so S2, I don't draw S2 on this picture, but there is the boundary of S2 which intersects S1. Yes, and what I will do is that I will remove from S1 the intersection with the boundary of S2, or a small neighborhood of this boundary mix. Okay, so this gives a surface with a bit more boundary components that it had before, because I did one boundary component for every intersection with the boundary of S2. So actually, this is a well-controlled number because this is just the linking number between the boundaries of S2 and S1. But I don't need this here. So this is how, so the Euler characteristic of this surface is what I defined as the punctured Euler characteristic of S1. And it depends on S2 because I removed the number of points which depends on S2. Okay, and then the thing is that then the Euler characteristic of S1 plus S2, so the sum of S1 and S2, so I take the interior of this surface, is just, by construction, the sum of these two punctured Euler characteristics. Okay, so the Euler characteristic is almost additive under this operation if you define it properly. And the thing is that just you look at what you did when you desingularize an arc here, you don't add anything on the Euler characteristic. When you modify, when the way it fails to be additive is at these intersection points where the interior of one surface intersects the boundary of the other surface. In a sense, when you have this, when you take the onion, you add 1 to the Euler characteristics. Okay, so it's almost additive, so you can compute the Euler characteristic, and then if you put back some disk along the boundary, you can compute the genus of this surface. And so, well, the Euler characteristic is almost additive, and the genus is almost additive, but not exactly, because you have to take care into account the boundary components, and this is where we can, where we can win some things. So just a quick example, if you take two sections of the Hopf vector field, so these are two disks. If I take the two disks from before, then I can take the union of these two disks. They intersect along an arc. I desingularize this arc. Yes, and what I obtain when I take the union of these two disks and I desingularize the arc is that I obtain actually an annulus. I don't know whether you see the annulus on the picture, but I take those two disks and I desingularize the intersection of these two disks, and this is what is called the Hopf annulus. So it's an annulus, and the core has self-linking, the boundary components have linking number +1. Okay, so here, for example, the Euler characteristic was 1 and 1 for the two disks. Yes, so we would expect an Euler characteristic of 2 for the union, but actually what we have to do is to remove 1 for each intersection point. So actually the modified Euler characteristic is 0 and 0. And hence, when we take this union, we obtain an Euler characteristic of 0, which is indeed the Euler characteristic of the annulus. Yes, so we did 0 plus 0 equals 0. Okay, but now you can play this game one more time because you can consider a third orbit of the Hopf flow. So you have a third disk, and you can desingularize the union of this thing. Yes, and in this way, what do you obtain? You obtain a 3-component Hopf link, so a Hopf link with 3 components. And if you take the surface, how many times will you have to desingularize? Well, the third disk you added intersected twice the previous ones. So now the modified Euler characteristic here will be -2 for the annulus and -1 for the disk, because the disk had Euler characteristic 1. But you removed 2 intersection points, so now it's -1, which means that now this 3-component Hopf link, it will have Euler characteristic -3. And since it has 3 boundary components, you know that it's a torus. So here we prove that the genus of a 3-component Hopf link is 1. And you can go on. Okay. The thing is that we can control the Euler characteristic and then the genus. Okay. Now, how can this be used? Well, now I will explain. Yes. I will explain how to use these ideas for Anosov flow, and I will add two more ingredients. So this process allows you to build a transverse surface inductively. You start from transverse surfaces and you take their unions. And if you are lucky, in the end, you will intersect all orbits. So this is how you can build a Birkhoff section from just local transverse sections. And this is the idea used by Fried in his proof that every transitive flow admits a Birkhoff section. He just used small pieces that I will explain right now and take their unions. And this is how you obtain a Birkhoff section. So the tool 2 is, what I call the Fried pens. So it's the following. I will explain it quickly. So I didn't speak so much about Anosov flow and their properties, but the main feature of Anosov flow is that they are Markovian. Well, one important feature, meaning that actually there exists a Markov partition, which is a finite collection of rectangles which are transverse to the vector field. And these are rectangles so that two sides lie in the stable foliation and two sides lie in the unstable foliation, which means that when you follow the flow, it's contracted in one direction and expanded in the other direction. Okay, so there is a finite collection of transverse rectangles which intersect all orbits. And there is an assumption on how the sides glue, but I will not use it right now. And such that, well, such that they are transverse to all orbits. And so in this way, every orbit is just encoded by the sequence of the rectangles it intersects. So if you have an orbit, you remember the infinite list of the infinite sequence of the rectangles it intersects, and it describes completely the orbit. And with the Markovian conditions I didn't explain, there is even a one-to-one correspondence between the orbits of a certain shift and the orbits of the flow. So you can describe everything of the flow like this. Okay, and here what I want to explain, the Fried pens, is if you take a point, I will call it X, inside a Markov rectangle, so there is an orbit through this point, and I want to explain how to construct a surface with boundary transverse to this orbit. Yes. So what you will do is that actually periodic orbits are dense in Anosov flows. So you may find two periodic orbits, one which is in the southwest quadrant with respect to X, so I will call this orbit, say, P, and one other orbit Q in the northeast quadrant. So you have, with respect to X, you have two periodic points. You can assume they are nearby, but it's not really necessary, which are on both in the opposite quadrant with respect to X.
When you say quadrant, they are separated by the stable.
Yes, sorry, I should have drawn this. Yes, here there is an unstable leaf here and a stable leaf here. So the quadrant corresponds to the quadrant delimited by the stable and unstable directions. Okay. Now the orbit P, it corresponds, as I say, to a certain word, and since the orbit is periodic, it corresponds to a certain periodic word. So there is a certain. So I will call RA this rectangle, meaning that in terms of words, the orbit P is encoded by a certain word AW1 to the power Z. So meaning that it's a periodic word, AW1, 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 and so on. Yes, I say it begins by A because I say that all orbits going through this rectangle corresponds to the letter A. Okay, and similarly for the orbit Q, there is a certain code which is a word AW2 to the power Z. Okay. And by the Markovian property I didn't really explain, we know that there exists an orbit whose word is just AW1, AW2 to the power Z. Because the admissibility of the word is just given by two letters syllables. So since the word AW1 is admissible, it means that after A, you may have the beginning of W1. After the end of W1, you may have a new A, and so on. So this word AW1, AW2 is an admissible word, meaning there is an orbit which follows these rectangles in this order. And now we can look at the two letters A in this word. They correspond to intersection points with our rectangle RA. And we may wonder, where are these intersection points? And what I claim, what Fried claims, is that these intersection points, they are in the two other quadrants. And the reason why they are in the two other quadrants is that the point corresponding to the first A, so where the word is AW1, AW2, for a certain time, it will follow the same path as the orbit AW1. So which means that it's almost in the same stable direction. Yes. And similarly, the word AW2, AW1, for sometimes it will follow the same direction as AW2, so it will be in the same stable direction. And more than this, it means that if you take the segments that connect P, which was in the southwest quadrant, to the word, I will call it R1, corresponding to AW1, AW2, this segment PR1, if you follow the flow, you come back to the segment PR2, to a segment connecting P to R2. Because after, when you follow these letters, after you follow the first letters, here you are back at AW2, AW1. So this is where the segment is sent. So this segment here is sent here. And similarly, the segment connecting Q to R2, so which the right side of this parallelogram will be sent on the top side of this parallelogram. Yes. So this is if you follow the flow. So now we have a parallelogram PR1QR2 with all its 4 vertices in the 4 different quadrants around X, such that if you follow the flow, the vertical sides come back along the horizontal sides. And now we take the surface, we consider the surface which is the union of this parallelogram plus these rectangles. So when you follow a side, when you follow the flow, it gives you a rectangle. So what we obtain is a picture that is made of 1 parallelogram horizontal and 2 rectangles which are tangent to the flow. So there is the left bottom rectangle, so it starts from the left side and comes back to the bottom. And there is the right one, which starts at the top side and ends up at the right side. So this is a surface here, which is made of three rectangles, 1 transverse to the flow and 2 tangent to the flow. Now you take. Oh, it's the other. Yes, sorry, Vincent. Thank you. So this one is not drawn correctly, because we start from the right side like this, and we come back with the back side. Okay, so is it better? Yes. So here we have a surface made of 3 rectangles, and the boundary, the topological boundary of this surface is made of 3 periodic orbits, the 3 periodic orbits we just considered. So now it's sometimes transverse, sometimes tangent to the flow. So you actually, if you smooth this, you can make it everywhere transverse to the flow. And here topologically, it's just a pair of pans because you compute the area characteristic. It's a sphere with 3 boundary components. So it's a pair of pans which is transverse to the flow and which contains the orbit through X, which is transverse to the orbit through the starting point X. Yes. So now what Fried does is just that he covers the whole manifold by such pair of pans. By compactness, just a finite number of them is enough to intersect all orbits. And then he takes the union, the iterated union of all these pair of pans. And this is how he obtains a Birkhoff section for any transitive Anosov flow. So from a Markov partition, he's able to construct a pair of pans. To get the existence of a Markov partition. Okay, and actually, just to remark that then the first return map is pseudo-Anosov because, in a sense, the invariant foliation it prints on the surface invariant foliations with singularities on the boundary, and we know that pseudo-Anosov maps are transitive. So it means that for a non-transitive Anosov flow, it cannot work. There is no Birkhoff section. Okay, so now. Just have 10 minutes left to explain so this is so the thing is that since the number of pair of pans here is not a priori bounded, you have no control on the genus. So if you want to obtain genus-one, well, then you have to be smarter in the choice of your pair of pans, and I don't know how to do that. So I will just explain a third tool, well, which is maybe a tool 2', which is a combination of these two things I explained. So the tool 2' is what I will call a Minakawa's pans. So it was explained by Minakawa, but may never published around 2013. The thing is that in some cases, so if you compute the genus here, assume that you started from a surface which had genus, I don't know, S, and you added a certain free pair of paths. In general, the genus of S will grow by at least one and probably more. Okay, but there is one circumstance where the genus will not grow. This is what I will explain. Assume that in the previous picture, so it's not anymore a local picture. You have your parallelogram P. So here is the vertex P of your parallelogram. Here you have the vertex R2, R1. But assume that R2, which is supposed to be here, thanks to the topology of the surface, assume that R2 is equal to R1. And so you have so assume that thanks to the topology of the surface, now the two opposite vertices R2 and R1 of the parallelogram are now the same point. So which means that we have a certain parallelogram which is, well, whose interior is embedded on the surface. So assume that now we are in a surface of section. We are in a transverse surface. We lie in the transverse surface. We look for periodic points and fixed points by the first return maps, which look like this. So we have three fixed points which are actually aligned, P, R, Q in this order, such that the segment PR is sent on another segment PR in the surface. So here we need to have a surface with some topology so that the new PR, well, so this is, for example, possible if we have a torus, and this will be indeed the case on a torus. Okay, so if we have such a rectangle, so assume that now P, R, Q are fixed points for the first return map. Yes, so exactly. So what I didn't exactly. So here we still have a pseudo-Anosov structure. So we have an invariant horizontal foliation. We have an invariant vertical foliation. And the first return map expands one by a constant and the other by the inverse of this constant. And so actually it means something to be aligned because there is a way of measuring the horizontal and vertical coordinates by the transverse measure to this foliation. So I didn't really explain this, but you have transverse measure for this foliation. So when you have an arc which is transverse to the foliation, it has a horizontal length and a vertical length. Actually, yes. So aligned means that the horizontal and vertical length of PR is the same as the horizontal and vertical length of RQ. Well, I mean, these horizontal and vertical, they give you coordinates, and then it means aligned with respect to standard coordinates. Just that a priori on the surface, there is no coordinates. But if you have these invariant foliations, then they are canonical coordinates. Okay, so if you have three fixed points which are aligned like this, and the parallelogram is embedded like this, then you can consider the freed sum of the first section you had plus these pair of pants. The pair of pants are freed here. And the miracle here is that the genus of this thing is actually just the genus of S. So you added something to the Euler characteristic, but the point is that you see here, well, S has some genus, but when I add the pair of pants, I remove 3 points from S. You remember we wanted to remove the intersection of the boundaries. So in a sense here, I will consider the Euler characteristic of S minus 3, because we remove 3 boundary components. Then we will add the Euler characteristic of the pair of pants, which is minus 1. Yes. So we obtain a surface whose Euler characteristic is chi of S minus 4. But it just turns out that in this thing, thanks to the fact that R1 is equal to R2, after the sum, in R, there will actually be 2 boundary components for the new surface. So actually, it corresponds to the fact that when I describe the boundary of when I describe what is an open book decomposition, I say that a page may arrive, for example, twice along a boundary component. Here, the page arrives twice around the boundary components R. So what it means is that actually the new surface has 4 boundary components, and so the Euler characteristic didn't really change, so the genus is the same. So here, this is a miracle due to Minakawa, that tells you that if you find a nice triplet of fixed points like that, then you may add something to your surface, but still same genus. The interest of this is that now, if you look at the first return map along this new surface, actually its dilatation, so the expansion of the stable and unstable foliation, has decreased. It has decreased because the first return time is a bit smaller. You see that the first return time is the first return time it was before, except when you are inside the parallelogram where you will intersect twice the surface. So the dilatation, which is a sort of renormalized first return time, is then smaller. Yes, and actually the set of the set of dilatations for pseudo Anosov maps on a given surface is an ordered set, is a well-ordered set. So if you have a sequence of dilatation which is decreasing, at some times you reach a minimum. Yes. So the strategy, I will finish by this, but so what happens? Let me summarize now. What happens is that now, if you consider Anosov maps on the torus, so Anosov maps on T2, well, I was a bit elusive on this, but here I consider only the cases of orientable invariant foliations. So here, Anosov maps on T2, they correspond to actually elements of SL2Z, and element of SL2Z with positive trace, with a trace larger than 3, actually, larger than or equal to 3. So Anosov maps on T2, they come from elements of SL2Z with traces larger than 3. And this picture of having 3 aligned periodic points like this, or actually you may even have P equal Q, it works as well. It exists as soon as the trace is larger than 4. So if the trace is larger than 4, then, and this was a remark by Minakawa, there exists a Minakawa spans, the Minakawa's spans, which means that if you consider the suspension of this map, so it has a canonical section which is just given by your T2, but now if you add a pent, you obtain a new torus which is transverse to everything, which is a Birkhoff section, such that the first return map has a smaller trace. So here the dilatation is correlated with the trace. And so if you have a given trace which is larger than 4, then you have another Birkhoff section with a smaller trace. And inductively, you reach a trace equal to 3. Yes. So inductively, you know that if you have a gene, so in the suspension of any Anosov map of the torus, you have a certain Birkhoff section whose first return map is 2, 1, 1, 1. Yes. Okay. And so this is why if you find one Birkhoff section of genus-one, actually you have infinitely many of them just by this process. Okay, and now let me just quickly explain how we go from genus-two to genus-one. Yes, and I will just finish by this. The thing is that these Minakawa's triplets, you can also look for them in genus-two when you have a pseudo-Anosov map on a genus-two surface. And here, computer experiments show that as soon as the dilatation is large enough, you always find this triplet of points. So this is an observation, and it can even be proven. And so actually, all pseudo-Anosov maps except 2 infinite families and a finite set of counterexamples, they have these triplets of aligned points, which means that then from this pseudo-Anosov map, you may find a new Birkhoff section with smaller dilatation. And then you are led to just 2 infinite families, which are very well understood, and a finite family of counterexample. And then the thing is that then you can look at these things, and in each of them, for each of these maps, in the suspension, you can find, in a sense, by hand, a genus-one Birkhoff section. And this is how we can prove the theorem for genus-two things. Okay, I will not explain. I mean, the detail is a bit complicated and computer assisted, so I hope to remove this assistance. But this is how it works. Yes, the assistance is to ensure to control the set of maps which do not have a triplet. So to ensure that almost but finitely many of them have a triplet, there is a proof which is very specific to the genus-two. Because the key point, in a sense, was explained to me by Erwan Lano and Vincent Delecroix, is that, in a sense, you can enumerate all pseudo-Anosov maps in a given strata, so with a given singularity pattern. But this enumeration works very well in genus-two, and as soon as the genus is larger, it's interruptible. I mean, there is a. This is really a big thing in well, I don't know, Schmuller theory or whatever, in translation surfaces, to have an efficient way to enumerate all pseudo-Anosov maps. So far, it only exists in genus-two. And that's the key here. Okay, so I stop here.
Any questions? So I've got questions about the dictionary between Anosov flows and contact geometry. So, but it's related to the proof that Etnyre explained in the beginning. For instance, for overtwisted contact structures, we have a geometric criterion, which is overtwistedness, that ensures the existence of a genus-zero open book. So maybe you could hope for a geometric criterion for Anosov flows guaranteeing the existence of a genus-zero supporting open book. But if you look at the John Etnyre's proof, then you'll be disappointed because the proof uses flexibility of overtwisted contact structure. So because of flexibility of overtwisted contact structure, you only need to prove that in each homotopy class of plane fields, you can build a contact structure supported by a genus-zero open book. So it's then you have to do this explicit construction. But maybe so probably this is hopeless for but maybe there is another proof could be more direct. For instance, when you have an overtwisted disk, you can prove that every Lagrangian link destabilizes, and this is a completely explicit thing. And you just bring the overtwisted disk next to your Lagrangian link, and then do a connected sum, and this is a destabilization of your Lagrangian link.
Yes.
So maybe the geometric proof of a more direct proof, like you start with any open book, you have an overtwisted disk lying around somewhere, and use it somehow explicitly to drop the genus of the
yes.
open book, and then maybe that could have a
yes. Yeah. Well, I don't know how much I understand what you said, because the thing is that, well, when you consider a contact structure, you have the flexibility of the choice of the red vector field, which is why you can deal with disks and here, well, since Anosov flows are structurally stable, I have some flexibility. I can perturb some things, but I fear we have less freedom. I don't know. That would be really interesting. The thing is that, well, this idea of stabilization and reducing the genus, I mean, if you take an arbitrary surface, usually it will increase the genus very much. So in order to decrease the surface, you have to work to look to find the nice surface.
This is why I talk about stabilization of the
genus. Yes. I understand. Well, I don't know what to say. Yeah, that's of course a nice idea, but
I'm not blaming it.
I don't. Yes.
Related in the opposite direction, you can explain why there are contact structures which are not planar, that have genus at least one, but so the proof was through holomorphic curves and
symplectization,
because if you have a genus-zero open book, then you can realize it
as a holomorphic open book. And then the question
is again, is there a version of this story for Anosov
flows that are not red?
No, I never thought about this, but that's a good question. I mean, even here, I take the assumption that the invariant foliations are orientable, and in a sense, this is a good way of preventing genus-zero. I mean, for an Anosov flow with orientable invariant foliation, there cannot be genus-zero Birkhoff sections, because that would print on a sphere something that is with invariant foliation are orientable. Okay, but then, okay, if you look at things with non-orientable foliations, or I don't know, I never really seriously thought about it.
Okay, more questions?
Any question from the remote audience?
I don't think so. Okay, thank you, Pierre, again.
Oui. Vraiment pareil. Oui. Non, mais c'est un truc que j'ai compris récemment. Parce que ça veut dire quoi? En fait, il y a un objet. C'est-à-dire, je regarde alors peut-être que personne, il y a un truc en conscience de et ça vous donne en fait une feuilletée par en fait, c'est un feuilletage qui n'est pas toujours séparé. Et donc, justement, ça s'appelle les choses à